This is the first in a series of videos about rate laws. We're going to talk about what a rate law is and how to write one, how to find the rate law from a data set, and a little bit more detail about the rate constant. So in our previous slide, or our previous video, we said that one of the 5 factors that affects the rate is the concentration, specifically the reactant concentration. So let's write that again here. The reaction rate is proportional to the reactant concentrations. And that is so important that we need a way to relate mathematically, specifically how much these two are related. Are they related by a factor of 1, by a factor of 2? Inquiring minds want to know. So let's put up an example reaction here. This example reaction is going to be super duper generic. A plus B sometimes goes to C plus D, where the lowercase letters are the coefficients and the capital letters are the names of the compound. So let's write a rate law for this, and you can see that I drew the double-sided arrow for equilibrium. So let's specifically write the rate law for the forward reaction. Since most of the time when you write the rate law, they will be looking for you to write it for the forward reaction. Okay, so here's the general anatomy of a rate law. It looks like the rate equals K times the concentration of each of the reactants raised to some exponential power. So K times concentration of A to the M power, concentration of B to the N power. This is our big generic rate law. So there's some unfamiliar things in this formula. So K, we haven't seen that yet. K is going to be our rate constant. And that is for some temperature T. Because as we said in the previous video, one of the factors that changes the rate is the temperature. So this rate constant is only valid for one reaction at one temperature. Seen these guys before? These are our reactant concentrations. So we want to include all of the reactants here, even if one of them ends up not being relevant because it has a 0 as an exponent. It's most correct to include all of them here. And then we have M and N, these exponents up here. These are called the reaction orders. And these reaction orders can be positive, negative, or 0. And they can be integers or fractions. So usually they're positive integers, but occasionally you'll run into a negative or a 0 or a fraction. So don't be surprised because those are definitely possible. So you can see that there's several different reaction orders, and so those are going to be the orders of each of those specific compounds. So M, we call that the reaction order of A. And so we could say that this reaction is first order in A. N is our reaction order of B. So we could say their whole reaction is first order in B. And then we can also get what's called a total order or an overall order by adding all of the different reaction orders together. So M plus N is going to be our overall reaction order. And we'll do some examples of those so you can have practice. And then one more point that's very important to make, notice that I use the letters M and N for these exponents. I did not use the letters A and B. So these coefficients A and B are not related to the exponents M and N. So the orders are not necessarily equal to the coefficients. We'll see a little bit later that sometimes they can be the same, but you don't want to assume they're the same. You need to use the data to determine the order. The orders are experimentally determined. They're not based on the stoichiometry. Okay, let's do a couple of examples practicing assigning an order to a reaction. So here's one. This is the one for the peroxide reaction we did in the last video. So the rate for that reaction is rate equals K times peroxide to the first. I didn't write it. You don't necessarily have to write the 1 up here. If there's nothing written, you can assume it's to the first power. So if I was going to describe the reaction order here, I would say this reaction is first order in H2O2, and that the reaction was first order overall. The sum of all the different coefficients is 1. Let's do another one with a few more things in it. This one is rate equals rate constant, some other rate constant, times hydronium concentration times hydroxide concentration. So this could be the rate law for some sort of a strong acid, strong base reaction. And so we can describe the order of each of the different reactants as well as the overall order. So we could say this reaction is first order in hydronium. This reaction is first order in hydroxide. And it is second order overall. You just add all of the coefficients together for that overall order. Okay, and let's do one more practice writing a rate law, because we only got to do it once. Let's write the rate law for the reverse reaction of what we did up above. So we've done equilibrium. We're professionals at going from the forward reaction to the reverse reaction. So we could rewrite it if we wanted, but I think we can do it in our head. So when we write the rate law, it's going to be rate, which we'll call reverse rate, so it's not confused with the first one, times some sort of a rate constant. And the rate constant is going to be different depending on which direction we go. So we'll call it the reverse rate constant. And then we're going to multiply it by the reactant concentrations. And so in the forward reaction, A and B were our reactants, but we're talking about the reverse reaction, which starts here and moves to the left. So C and D are going to be our reactants for the reverse reaction. So concentration of C and concentration of D. And we know that the coefficients are going to have nothing to do with the stoichiometric coefficients, and they're going to have nothing to do with the forward reaction coefficient. So we need to make up some more letters here. We'll call it P and Q. Those can be the coefficients. They're unknown. So pretty straightforward, writing this reaction in the forward direction or in the reverse. Remember that the rate and the K value are going to be different. Sometimes we like to write it. So over the forward arrow, we'll write K forward. We'll give a name to that rate constant. And over the reverse arrow, we can write the name of the reverse direction constant. Those are for a little bit later. Okay, so we've done a couple of examples, and The final big point here is that rate laws and everything in them, the rate constant and the orders, they're experimentally determined. Everything we know about rate laws, we have estimated from huge repeated data sets. Every rate law is essentially half of a graduate student's PhD, repeating that experiment over and over in lots of different conditions to be really sure about that rate law. And the way we can determine the rate law is by looking at the rate. Specifically, the initial rate. So we look at the initial rate at different reactant concentrations. So we can change the concentrations we plug into our rate law. We could pick 1 and 1, 1 and 2, 2 and 3, 0.1 and 0.2. We can pick lots of different combinations of initial reactant concentrations, measure the rate law for each, and that allows us to solve for our unknown variables. The unknowns that we need to use the data to give us are going to be our rate constant, K, and each of those reaction orders. So depending on how many reactants you have, you may have more things you need to solve for. If you have a reaction like this one, you only have to solve for 2 things, the order up here and the rate constant. But if you have a reaction like this, you have 3 things to solve for. The more reactants you have, the more unknowns you have to get from your data. So in the next video, we'll take a look at a data set and we'll try and derive the rate law from that data set and talk about how we solve for each of those different unknown variables.